Okay, it's
Recording
almost
in progress.
okay, great. Recording is in progress, and I'll go ahead and start. It's an honor, and thank you, Olga, and all the organizers of this workshop for giving me the pleasure to chair this session. And the first speaker is Philip Russell, director of the Max Planck Institute for the Science of Light in Erlangen, Germany. And I don't want to take any time from his talk, maybe just 1 minute. And I want to tell you a few words about his career, Doctor of Philosophy from Oxford. And then basically he just moved back and forth between UK and Germany with a period of about 10 years on average, I would say. From UK, he went to Hamburg as a Humboldt Fellow, then back to Southampton. And that's where he started his work on photonic crystal fibers. This is what he is famous for. And please notice how fibers are properly spelled on that side of the Atlantic. 1996 was the year, I believe, and he can correct me, where photonic crystal fibers were finally demonstrated. The longest holes, the longest man-made holes in the universe. And of course, it's not just the length of the holes that makes them special. It's this structure in the transverse direction that can be custom made and designed to achieve whatever is needed for optics, nonlinear optics, and so forth. After Southampton, he moved to Bath, spent his 10 years there before moving to Erlangen, Germany, and basically establishing the Max Planck Institute for the Science of Light there. Over the years, he won all possible awards. I will not dwell on those. Again, what he's famous for are these photonic crystal fibers, and he's pushed that science and technology through various breakthroughs. I'll mention a couple of his distinctions. He's a fellow of the Royal Society, and he was a president of OSA, now called Optica, during the International Year of Light of 2015. I think that's enough for an introduction, and I'll stop sharing so that, Philip, you can share your presentation.
Yes. Can you see it?
Not yet.
Okay, I'd better start it again, I think. There. Yeah.
Okay.
Yeah, it should be coming up.
Yeah, now I see
so
the first slide.
You see the first slide?
Thank you.
Okay, thank you for the nice introduction, Alexei. Good afternoon, good morning, whatever it is, wherever you are. And thanks to Alex for the invitation to give this talk at Laser Physics. Actually, I did give a talk at Laser Physics way back in 2003, and that was when it was held in Hamburg. And Gunther Huber invited me to give a talk about PCF. In fact, it was one of the first talks about photonic crystal fibers at a conference. So what I'd like to do today is cover some of the basics of a new kind of photonic crystal fiber, a chiral photonic crystal fiber. And I'd like to I'm planning to touch on some recent results on a new kind of light localization in chiral coreless PCF, which is what you're seeing on this slide. These rotating patterns are, in fact, localized optical modes in a coreless fiber, the fiber that has no structural core. I'm going to come to that later in the talk. But first of all, I'd like to get into understanding what light does and how it behaves in chiral waveguiding structures, and particularly analysis of n-fold rotationally symmetric rings of chiral cores as a first topic. So just to kick this off, it's good, I think, at the beginning to understand what happens to light when it's guiding in a single mode cylindrical or circular waveguide core, which is following a spiral path. In this particular case, provided the twist rate, this alpha is the twist rate, 2 pi over the pitch. If the twist rate is not too big, it's quite gentle, then the light, if you launch in linearly polarized light into this kind of system, it almost ignores the twist. It almost comes out pointing in the same direction, the linear polarization state. But the one difference, it's slightly rotated. It's rotated by a small amount. And when you have rotation of a linearly polarized signal, this can only be caused by circular birefringence. And in fact, you can easily show that the rotation angle of the electric field is proportional to the circular birefringence in this case. This small optical rotation is actually very small. It's proportional. The birefringence is proportional to the cube of the twist rate. Very strong dependence on twist rate and on the square of the radius, how far the core is from the axis. And for example, if you have a helical pitch of 5 millimeters, these are typical parameters at a wavelength of 1 micron, we get a rotation of about 2 degrees per meter in this case. But the really important thing about this slide is that the modes the eigenmodes of this system are circularly polarized. So if you launch in right circularly polarized light, it will come out right circularly polarized. That's the most important thing that I want you to take from this slide, because all the modes I'm going to talk about in this talk are circularly polarized. So let's talk, however, I'm going to step back and let's talk about an untwisted ring of coupled cores. So this is a photonic crystal fiber. These dots here are the hollow channels, and there are there's 6 solid glass cores in the structure, evenly spaced around the central axis. And this is an untwisted fiber in this case. How would we analyze a system like this? Well, obviously, these are coupled cores. You can analyze them using Bloch theory. We can assume nearest neighbor coupling, set up some coupled mode equations. The amplitude in the nth core, the rate of change of that is with distance along the fiber is proportional to the amplitude itself with some kind of propagation constant adjustment, which would be the eigenvalue. And it's coupled to the neighboring cores, the n+1th and -1th. And if we assume there's a Bloch mode in there, there'll be a Bloch phase between the cores, phi b. So the n+1 will be plus phi b and n-1 will be minus phi b. And we end up within this cosinusoidal dispersion relation, essentially, between gamma and the Bloch phase. Okay, so this mode travels along. This is a mode that's going to be carrying angular momentum, in fact, because the intensity in each core is constant. It doesn't change. So the mode pattern doesn't change. But what does change is that there's an underlying phase progression around the ring, which is caused by this Bloch phase. And if we plot out the dispersion relation that results from this, so this will be the axial wave vector of the modes versus the azimuthal order. And I didn't explain azimuthal order. Let me go back. Azimuthal order LA here is the number of, it's an integer, it's the number of 2 pi's of phase progression when you go around the azimuth 1 time. So you go around the azimuth, say, once, and LA is 3, then you'd have a 6 pi phase progression in that case. Okay, so that's the azimuthal order. And it turns out that this system, because it's a closed circle, a closed cylinder, the phase around the loop here LA has to be an integer for the mode to exist. So this means that only integer values of this azimuthal order are possible. And for a 6-fold rotationally symmetric system, you go from -3 to +3 within the first Brillouin zone. So that we get this cosinusoidal shape of the dispersion curve. And there will be, for example, these 2 Bloch modes, or helical Bloch modes, as I like to call them, which progress in a clockwise direction. And we have ones that progress in the anti-clockwise direction. And of course, they have identical propagation constants and so on. So this is the picture I'm going to be using, the basic picture. But of course, what I want to do is treat a chiral system of 6 chiral coupled cores in a ring. You could view this as a kind of propeller PCF, because if you put light in, the light is forced to rotate. It's forced to kind of spin as a result. So of the twist. The spiral paths, as I've said already, yield circular birefringence. So we can assume that the modes are circularly polarized and the polarization state is maintained in this type of system. So how can we treat a system like this using coupled mode theory? Well, if we just look at two of these cores and just place them here, they're going to be slanted. The slant's in the opposite direction. Sorry about that. Doesn't really matter, though, for the analysis. We have core 1 and core 2 that are adjacent cores. Coupled mode theory will apply for amplitudes that lie on this line AA, which is normal to the two waveguides. So that's normal coupled mode theory. But what we want is a coupled mode theory that applies to the amplitudes B1 and B2, which are in the transverse plane, where phi is the direction of the angle around the azimuth. So how do we set up these coupled mode equations for the amplitudes B1 and B2 that are defined along this phi axis? Well, we have to introduce a path length correction. We have to pull the A1 field back to point B1, we have to pull push A2 forward to B2 by introducing a path length correction. It's quite simple to do this. It's just if you take the average of sigma 1 and sigma 2 here, we can set up the equations. They look like this. There is a slight increase in the sine theta underneath this theta here. This theta will increase the coupling rate, or you can also view it that the path length is increased because of the tilt. This is actually quite important in some of the discussions later on, this sine theta. Anyway, we then have to apply an azimuthal resonance condition in the transverse plane to the amplitudes B1 and B2 and so on around the ring, and then we can derive the helical block modes of this system. You can actually use a more rigorous analysis, and this will allow you to work with fields that are not just circularly polarized, using a local Frene-Serre frame of unit vectors that tilt and twist according to the spiral path of one of the cores. So there'll be a tangential unit vector, a normal unit vector, and a binormal unit vector in this system. You can actually develop quite a nice analysis based on this, as is explained in this reference at the top here. Okay, I'm going to come back to this in just one slide, but I'd like to spend a little time just talking about circular polarization state, orbital angular momentum, spin, and topological charge, because this is going to be important to what I want to discuss today. So I've already explained what azimuthal order is, but I didn't talk about the polarization state of the light and so on, and where this LA actually comes from. If you solve Maxwell's equations, as many of you will have for any kind of cylindrical system, you will, including an optical fiber, of course you use cylindrical coordinates. You use a cylindrical coordinate system. So you'll have the radial coordinate, you'll have the azimuthal coordinate, the angle, and the z coordinate along the axis. Because of that, the LA comes straight out of Maxwell's equations, this azimuthal order, but it applies to a cylindrical coordinate system. So the picture in the middle here, this one in the middle, it would have azimuthal order of 0, because the electric fields at this particular instant in time are all pointing in the radial direction. So they're all in phase when you solve Maxwell's equations. Of course, there might be some spin as well if it's circularly polarized. And you'll also notice that under these conditions, the fields on opposite sides will cancel on axis. So we get a singularity on axis. We get a 0 field. We have to have 0 field on axis under these circumstances. If we go to the case where the azimuthal order is plus 1, then we end up with the system on the left here, where all the fields are pointing in the same direction. And there are no singularities in this case. And to the parameter I use for the number of singularities is the topological charge. So in this case, the topological charge is -1, which is azimuthal order minus the spin value, plus or minus 1. And in this case, there are 0 singularities. So it's, if you like, the field is uniformly polarized right across the core. And we could go to the case where LA is -1 and spin is +1, and then we get 2 singularities in that case. Now, we can apply this to the system of 6 cores. This picture works perfectly well. What the azimuthal periodicity does is to produce harmonics. So we not only have topological charge of, let's say, whatever it is, -1 in this case, we'd also get -7 and +5 just by adding 6, which is the number of cores we get. And you can get very, very many harmonics in a system like this, it turns out, as I'll show you in a minute. Okay, let's come back to the Strene-Serre analysis. If you run through the analysis and solve the equations for this system, we end up with dispersion curves that look like this. The dispersion surfaces are tilted, as we would expect to see. The left and right circularly polarized fields are these two different colors, red and green. They almost have exactly the same shape, except they're shifted from one another by 2 in azimuthal order. And this is a consequence of the spin being plus and minus 1. If we take this system and we plot instead against azimuthal order, we plot against topological charge, then these two curves move on top of each other. So we go from the separated curves to curves that sit on top of each other, but with a very small circular birefringence that I discussed already. So there are actually two curves here, but they're so close to each other, you can view it as one, again, for circularly polarized fields. And we can see right away here that for LT is plus and minus 1, for example, the +1 and the -1 topological charge modes, which would have exactly the same propagation constant in an untwisted fiber, they have radically different propagation constants in this case. And this gives us an additional lever to play with for all kinds of different devices that you want to design. And also in nonlinear optics, there are many opportunities. This analysis gives rise to a relatively simple analytical expression, which I'm not going to just talk my way through. It would take far too long, except to point out that the dispersion relation, the propagation constant of the nth harmonic of the helical Bloch mode, is given by this expression, and you get the topological charge appearing here in the expression. And the only place where the spin appears is in this term here. It only appears explicitly in this term here, which is the circular birefringence term, which is very small. So this is a very useful expression for plotting out the dispersion surfaces, as we see, for example, here. Let me just get this going. So we could, for example, at 0 twist rate, this is what the curves look like, left and right circularly polarized fields, and plotted against topological charge, we get almost the same curve. And then as we increase the twist in both directions, you see the curves stay at the same height, more or less. But they have to do that so that when they are displaced left and right, they sit on top of the white dashed curve here. Okay, so I'll show you some experimental results. This is a twisted photonic crystal fiber with 6 cores in a ring, just like in the picture here on the top left. This would be the dispersion surface I just showed you against topological charge. This is an experimental measurement of the LT topological charge -2 mode, which corresponds with this dot. Okay, and this is created by interfering a divergent Gaussian beam with the mode coming out of the fiber. And you see a double spiral in this case, as you would expect, because the topological charge is -2. Topological charge -1, we get a nice clean single spiral corresponding with this dot, and +1 and +2 and so on. So it all agrees very nicely with the theory. One interesting thing about these plots is if you look at them carefully, you notice there are some off-axis singularities in the field, these fork-shaped things, so the single fringe turns into 2. These are caused by the Bloch harmonics, so that I was talking about. So these are harmonics that are outside the first Brillouin zone that cause these additional features. Okay, so now let's talk about an application of this to chiral Pl.4 photonic crystal fiber. These are optical fibers where we observe circular dichroism, where left circularly polarized light has higher loss than right circularly polarized light, or the opposite. And also talk about vortex modes. So the kind of fiber we've been working a great deal with recently are what we call single ring photonic crystal fibers. These are very simple structures. You can read a review about them here in this paper from 2017, though there have been a lot of more recent really good advances in this field published. I'm not going to talk in detail about this today, But it's a fiber with thin-walled capillaries that are placed in a ring around the central hollow core. This particular fiber just happened to have 5 capillaries. There's no particular reason for that. There's a picture of the fiber. It actually looks like you can see it's twisted along its length. So we make these fibers, by the way, by spinning the fiber preform during the fiber drawing process. And what we observed in the experiment was that the right circularly polarized fields launched into the core saw a very high loss, whereas the left circularly polarized modes saw just the background leakage loss. So there was a massive increase in loss for one of the circular polarization states. And modeling agreed with this. This was nice. You might say that's the end of the story. The modeling agrees with the experiment, but being the kind of person I am, I want to understand why. So we spent a long, long time trying to understand what on earth was going on here, and it was actually very difficult to explain it. So I'm now going to tell you the explanation for this effect. So let's have a look at the mechanism underlying this circular dichroism. Once again, this is the axial refractive index of the modes versus the azimuthal order. You've seen this plot before. It's a 5-fold symmetric structure. So the Brillouin zone has a width of 5 in terms of azimuthal order. And this would be the propagation constant, the refractive index, if you like, of the core mode for the spin -1 and spin +1. So now let's think about these capillaries that are in a ring. These capillaries are coupled with each other, and they will form a helical block mode in the ring, just like I explained a moment ago. So we're going to get dispersion surfaces like the ones I showed you before. So this is a very similar kind of animation to what I showed you before. So in the untwisted fiber, we'd see this, that the core mode is not phase matched to any of the ring modes, and we get low loss. If we change the twist rate, we'll reach a point here where the S equals -1 mode of the capillaries will phase match to the S equals +1 core mode. Now those modes are orthogonally polarized, so they won't couple, they won't talk to each other. At least you would think that on this simple model. We can then go further in the twist rate. We find a point where the core mode and the mode in the ring are phase matched, but this does not give you circular dichroism because both +1 and -1 modes are phase matched to the ring. So both will see very high loss. So we come back to this point. At this point, we have phase matching for one of the polarization states in the core, but not for the other one. So the dichroism has to be connected with this particular condition. And in fact, when you do full numerical modeling of the system, you find that the modes are not perfectly circularly polarized. In fact, the polarization state in the regions where the capillaries are talking to the core mode, the polarization states there are much more complicated. They're sort of elliptically polarized in general. So it then becomes possible for this coupling process to take place, and this gives rise to the circular dichroism. Okay, so just one final slide on this is the guidance of vortex modes in the hollow core. This is a lot of people working with vortex modes these days. We have found that you can very nicely guide in a hollow core like this. You can guide vortex modes. Here's an example of a topological charge +1 mode with a single discontinuity singularity on axis ring mode in the core, guided in the core. We use a spatial light modulator to create the patterns in this case. But we were also able in this case to launch in modes with topological charge +2 and +3. And one really beautiful thing about this experiment, which I just love this result, is that the singularities are actually separated. And the reason they're separated is because the structure isn't perfect. It's not perfectly 6-fold symmetric. As a result, the zeros in both the experiment and the finite element modeling are separated. And this is also true of the case where you have 3 singularities. And so you can start to play games with thinking, how does the phase work here? We have to have a 4π phase change around the center. So you have to encircle each of these singularities once in order to end up with 4π. And you have to do it twice down here to end up with 6π. So I think it's rather a nice observation. We did all kinds of work, by the way, filling these fibers with hydrogen and playing around with the interaction between these vortex modes and in stimulated Raman scattering. Okay, another topic. Again, this is a topic of nonlinear optics. This is forward stimulated Brillouin scattering in chiral photonic crystal fibers, in which we have observed the coupling between vortex modes by means of chiral acoustic waves or chiral phonons, and also demonstrated non-reciprocity. So let me just jump straight into this. Guided wave stimulated Brillouin scattering has in recent years become a kind of hot topic. There are many groups working on this, lots of papers, two very nice tutorial review papers if you're interested in following the field, they're quite recent. Forward stimulated Brillouin scattering is between two forward propagating modes. This has been observed in hollow core photonic bandgap fibers filled with air. They've been observed on silicon chips. They've been observed in polarization maintaining fibers, standard fibers, many different examples. We did report, my group here in Erlangen did report backward Brillouin scattering in chiral multicore PCF. This is a PCF with a Y-shaped core, as you can see from the scanning electron micrograph. In this particular case, we launch in pump light with a certain spin and a certain vortex, a certain topological charge. It would then be scattered into a backward Brillouin signal, which has the opposite values of topological charge and spin, because they both have to spin in the same direction, but because the Brillouin signal is going backwards, it's kind of has the opposite topological charge sign. Anyway, that's not what I want to talk about today. I want to talk about the forward scattering process, and in particular, intermodal forward Brillouin scattering. To illustrate this, here we have a dispersion plot of axial wave vector versus frequency. And there's going to be a fast mode in the system and a slow mode in the system. The fast mode has a higher refractive index, a higher wave vector beta than the fast. And there'll also be a phonon, an acoustic mode guided in the system, a phonon of some sort. And this would be the phonon dispersion relation. This is a few gigahertz frequency range, and this, of course, is hundreds of terahertz. This is the optical frequency up here. Let's suppose we have some pump light at a particular frequency. We turn off the power in this system, if you turn off the power sufficiently high, you could potentially get stimulated scattering into the Stokes mode at a different frequency. But typically, we have to seed the Stokes mode in this case to see this effect. But anyway, we create a phonon that has a certain wave vector and a certain frequency. And it's the slope and the length of this phonon 4 vector. It is actually exactly connects the fast and the slow branches. So we can then couple light from the pump light to the Stokes, from the pump mode to the Stokes mode, from the slow mode to the fast mode. One example of this is scattering from the LP01 mode to the LP11 mode of an optical fiber using flexural phonons. So this is a flexural phonon that oscillates in one plane, as you can see in this animation. You can also see a similar effect, interpolarization scattering between vertically and horizontally linearly polarized modes in a system. And this happens if you can excite a torsional phonon, as is shown in this animation. And then the topic that I'm talking about right now, which is intervortex scattering using phonons that have orbital angular momentum, or I like to call them corkscrew waves. In fact, you can create a corkscrew wave like you see in the bottom animation by superimposing two of the ones at the top, these flexural modes, one which is oscillating, is vibrating in the vertical plane, the other is vibrating in the horizontal plane, and you introduce a pi/2 phase shift between them, you would end up with a corkscrew wave that looks like the one at the bottom. You've seen this animation before, but discussing polarization state and so on in the context of this Y-shaped core, because there is a central core in the system, there's some glass in the middle, we're going to have a fundamental mode that's concentrated right on axis in the fiber. This will have topological charge of 0. There's no discontinuity in the field on axis. There'll also be modes that are localized in satellite cores. One of these will have topological charge of 0, would look like this. And this will hybridize with this mode or can hybridize with this mode because the topological charge is the same. So they can talk to each other. They might be phase mismatched or whatever, but they can hybridize. And then we have topological charge plus and minus 1. It's threefold symmetric. So the Brillouin zone is only 3 wide, so we only have 3 modes in the 3-core system, and these would then be topological charge plus and minus 1 in the system. Okay, let's have a look at some of the results here. So this is an experiment where Jinglin Zheng, who did the experiments, launched in a pump light in the fundamental mode and a Stokes signal at topological charge of -1 into a system like this. So this is the pump and this is the Stokes launched in. In the system, some kind of corkscrew acoustic mode was excited. There's a finite elements simulation of what the mode might look like. As a result, we were able to convert power from the pump light to the Stokes light, as you can see here. And in fact, we got up to 20% conversion. The fiber length in this case was 8 meters, so it's a fairly weak effect, but nevertheless, as you can easily see it in the experiment. So what we did next, or what Jinglin Zheng did next, was to demonstrate a non-reciprocal device using intervortex conversion. And I produced a simplified plot here just to illustrate this. We once again have a fast and a slow mode in the forward and the backward directions. In this system, if you could excite one of these corkscrew phonons using pump light and Stokes light, so putting 2 signals in to deliberately drive this acoustic wave, so we create this acoustic 4 vector, then because of the shape of these dispersion curves or lines, we can reuse this phonon that we just created. We can use it to cause coupling in the backward direction between a pump and a Stokes mode, because we can get perfect phase matching if we do things correctly. But in the forward direction, this 4 vector is unable to cause coupling between the fast and the slow modes because we have a large amount of dephasing. And in fact, in the experiment, we saw practically no conversion in the forward direction because of this dephasing, whereas there was strong conversion in the backward direction because we're phase matched there because of the shape of the dispersion curves. These are some of the parameters in the system. We had a non-reciprocity factor of about 14 dB in this case, and a maximum conversion efficiency of about 20%. Okay, so that was forward Brillouin scattering, and this brings me to what I talked about right at the beginning, which is a new type of field localization that occurs in chiral waveguide arrays. Field localization has been studied for decades. Of course, it goes right back to localization of electrons, Anderson localization. But then people rapidly picked this up in the context of optics, and there are some papers that are certainly worth looking at if you're interested in following the field, and all kinds of beautiful pictures of light localization you can see in these papers. Actually, right at the beginning of photonic crystal fibers, the very first fiber that we made in my team, that was at the University of Southampton actually back then, we weren't sure this would ever work. So the very first fiber we made didn't have a core, but it wasn't particularly nice. As you can see, the periodic structure is pretty messed up. There's lots of irregularities and so on in the structure. And in fact, it did guide light, but randomly guided light. So this is like light localization in a disordered PCF. We didn't actually publish this because we didn't think it was interesting. But then subsequently, a couple of groups have looked at this type of random system and explored it in more detail. Anyway, that's just a brief introduction to the localization of light. So what about light localization in a chiral array of coupled waveguides? Well, actually, this has already been observed. We spent several years studying coreless PCF. Coreless, that means there's no structural core. There's just a regular array of guiding cores in the structure. When you helically twist it, a fiber like this, it actually will guide light close to the axis. And these are measurements made by Paul Roth, who was a postdoc in my group. He also did his PhD with me. He did some beautiful measurements of the modes. These are measurements of different modes that he was able to find. and agree very well with simulations. And you'll notice something interesting about these modes, which is that the field lobes are very distinct. There are distinct field lobes with a certain kind of pattern. I mean, this pattern here is a graphene pattern of field lobes. The pattern up here is more like a honeycomb lattice of rings. And down here, we have a Kagome pattern of field lobes. He also, by the way, measured the harmonics, the helical block mode harmonics of these systems. And as you'd expect, there are so very many harmonics because it's quite a complex structure. And if we look at the Kagome lattice, for example, there are harmonics, the minus 19th harmonic, plus 23rd harmonic of the helical block mode. So it's interesting to see that. Anyway, that's not the point of this. What I want to do now is, these were observations. They agreed with simulations. But once again, I wasn't content because it seemed to me we didn't understand exactly what this guiding mechanism was. Simulations is a kind of experiment. I mean, it doesn't help your understanding necessarily. So we went about applying coupled mode theory to pairs of coupled cores, so treating these blobs of light, these antinodes of light as coupled cores. Now, to do this, we needed to generalize the coupled mode theory I talked about a moment ago, or a little while ago, for a pair of spiraling waveguides that are at arbitrary positions in the cross-section of the fiber. So they'd be at different values of radius, rho 1 and rho 2. They would also be at different values of a different angular spacing in general. And then the fiber, of course, is chirally twisted. Now, if we look at this system and you think about it, it took me a while to realize this, but coupled mode theory, normal coupled mode theory will apply to points B and C, where you can draw a line that is perpendicular to both waveguides and where the spacing between the two waveguides is a minimum. And normal coupled mode equations apply there. If you want to pull back the amplitudes into the transverse plane, so points A and B, then what you have to introduce is a path length correction that will involve the delta phi and will also involve the two values of radius. And it turns out you can do this quite easily. The coupled mode equations look like this. We now find there is a dephasing parameter, and that's because the path length of the blue core will be longer than the path length of the orange core because it's further out and it's more stretched. So there's a dephasing parameter, very important. And we also have the path length correction factor, which takes a quite simple form. It's shown here. That goes into the coupled mode equations. So the reason for these parameters being more complicated than in the simple case is because we have to take account of torsion as well as the tilting. All these parameters have to be included in this model. It's really quite simple, though, in the end. And so we have a general pair of coupled mode equations that should be valid for an arbitrary pair of cores. Now, let's think about a system, a simple system of 160 cores arranged just in a row. It's not actually along a radius. This is just with no twist in this case. And you solve the coupled mode equations for this system. You can find all the modes of the system. There will be the fundamental mode that has a single lobe. Each of these blobs, each of these circles is one of the cores, by the way. And we can get modes that mode m equals 10, 150, and so on. There is no field localization here. The field patterns resemble planar waveguide modes, in fact. If we twist the structure, so we take the cores and we twist it into a structure that looks something like this on the left, then we find a mode that is localized close to the axis, the fundamental mode. Again, each of these circles is one of the cores, and it's exponentially localized. This is an exponential drop-off in the intensity in the cores. This is on a linear scale. We see a well-localized mode close to the axis. The 10th mode looks like this. It's spread out over many cores because actually close to the axis, the twist has only a quite weak effect. So the dephasing parameter between the cores is quite weak. So the mode is fairly spread out across the cores, but once again, it's exponentially localized at large values of radius. And we move out, then we find that the 50th mode is exponentially localized both towards the axis and to higher values of radius. So these are genuinely localized modes in this system. and we go up to the 100th mode, we go to the 150th mode, you can see that the modes are becoming more and more localized as we move further out. And this is because the dephasing between adjacent cores increases as the square of the radius in this case. So this system shows clearly we can get localization simply by introducing a chiral twist to the system. And this can also be applied to helical block modes in a hexagonal lattice, for example. So just to show you how this works, this would be the twisted structure with no core, no structural core. To calculate the field amplitudes in the XY plane, we have to introduce the path length corrections I was talking about for each pair of cores. We then apply Bloch's theorem from one sector to the next. You can work out the number of coupled mode equations, there's a number of cores and so on. So the analysis is straightforward. The matrix is big, but it's quite sparse, and it can be solved extremely quickly with just a few seconds compared to days when you do finite element modeling. So let me show you some results. So this is a hexagonal lattice of cores. These are the guiding cores. These are the results that we get for the propagation constant, the refractive index of the helical block mode as a function of topological charge. It's six-fold symmetric, so it's -3 to +3 in the first Brillouin zone. These full curves are the analytical theory, and the dots are the results of finite element modeling. It looks a very complicated tangle of curves, but we get almost perfect agreement between the finite element modeling and this simple analytical model, which only takes a few seconds to calculate. And the modes themselves, you can see patterns down below here. They spread out more and more as the refractive index goes up of the modes, and for different topological charges, we get different patterns. So there's huge numbers of different modes that are localized in this chiral system, and they're actually exponentially localized. In this particular case, we get a localization rate of 12 dB per period in terms of intensity. If we have a look at the Kagome lattice of close-packed honeycomb lattice of coupled cores, we get this result. Once again, excellent agreement with finite element modeling. And these are some of the mode patterns we see, and is exponentially localized with -19 dB per period. And finally, a honeycomb lattice, which is basically a graphene lattice of coupled cores. This gives you the best field localization of about -22 dB per period. And these are some of the patterns you can see. So there are modes that are localized close to the axis, but we also get modes that are localized in a ring, rather like the modes I showed you in that linear array. And there's one final picture is what happens as you increase the twist rate for the honeycomb lattice, just the last one I showed you. As the twist rate increases, the modes get smaller, as you would kind of expect, I suppose. But what's quite nice about this, if we look at the +3 topological charge, the mode with the topological charge +3, it will also have a -3 harmonic. And the +3 and the -3 have the opposite topological charges, and they're going to be reasonably comparable in amplitude. So you'd expect the topological charges to cancel and give you no field singularity on axis, which is what you see here. Whereas modes where there's an imbalance, say the +1 and the -5, will have quite a distinct field singularity on axis. So there are all kinds of interesting patterns that come out of this analysis. Okay, just final slides. I believe this new theory introduces opportunities for new studies in nonlinear switching, for example, discrete spatio-temporal solitons, self-organization of light within complex systems of coupled cores. It's also interesting that both the effective nonlinearity and the dispersion increase with the square of the radius in systems like this. You can also directly integrate the coupled equations from an arbitrary initial condition, provided, of course, that you avoid numerical instabilities that can happen in a system like that. You can treat arbitrary arrangements of cores, even those that don't have any rotational symmetry. There's just an example of a clover leaf pattern of cores and some of the modes that appear when you make a chirally twisted photonic crystal fiber. It's not, well, is it a photonic crystal? I'm not sure. But you make a fiber with an array of cores like this, you can get all kinds of interesting mode patterns. So just at the end of my talk, so I'd like to acknowledge the work of Gordon Wong, who was the head of the team running the PhD students and postdocs working on this over the years. And of course, very important, the fiber fabrication team that made the fibers we worked with. So thank you for joining the talk, and that's the end.
Thank you so much, Philip. Thank you. We have time for questions. Let's see. Vitaly has his hand raised.
Thank you for the great talk. My question is about the non-adiabatic mode coupling in this multi-mode system. Obviously, you have the situation when different modes have the propagation constants which intersect at some point, and therefore they can non-adiabatically couple. Was this effect observed and used? Because it can be used positively, but also can affect the depolarization and other negative effects. Could you comment on this?
I think, were you thinking about this dichroism result, perhaps, of circular dichroism? Because in this case, you do indeed get, you can find points for a certain twist rate where the core mode in this holocore fiber system is able to couple to the mode of the capillary ring and give high loss for one polarization state, whereas the other circular polarization state doesn't see high loss. So yes, I mean, absolutely. I mean, as you change the twist rate, the phase matching between the central core and the ring in this case will change. And at a certain twist rate, we can achieve phase matching or not. And that could cause loss. Maybe we don't want loss. So you need to avoid those points, of course. But yes, absolutely. I mean, the twisting does allow you to adjust these phase matching points and to control the amount of loss in the system or increase the amount of loss in the system if that's what you want to do. And you can do that mechanically too. You can actually apply a torque to the fiber and twist this effect. So it gives you the ability to maybe fine tune these resonances or these loss regions. Yeah.
Okay.
Thank you. Let me ask a quick question regarding these phonons in forward Brillouin scattering. I'd like to understand a bit better the nature of these phonons. They're optical phonons and they're propagating. So what's their characteristic?
No, they're not optical phonons. No, these are acoustic. These are acoustic phonons.
What is their characteristic propagation lengths or lifetime?
In the forward direction is a good question. We haven't measured that, but they do propagate quite far. I mean, they're in the gigahertz range, so it's not 10 gigahertz, but they don't. I would say they propagate a few millimeters at most. In the system. I think there's some parameters here just to show the acoustic wavelength of these corkscrew phonons is 45 micrometers in a fiber with a twist period of 5 millimeters, for example. And the frequencies, in this case, it's only 100 megahertz, this particular mode. These flexural modes tend to be quite low frequency. Because the whole fiber is kind of it's more like a rope than a stiff piece of glass. So they tend to be quite low frequency waves. I mean, to be honest, we still have some work to do to identify exactly which phonon is causing it. I mean, there's an animation of the finite element modeling of the axial displacement of what we think is the mode that's causing this coupling. But what is certain is that a mode which an acoustic phonon has to exist that is a vortex phonon. Otherwise, you can't conserve angular momentum in this system. But there's still more work to be done to understand this. So you're quite right to ask.
Okay, thank you very much. I have more questions, but it's time to move on, and I don't see any other hands raised. So let's move to the next talk.
Okay.
Thank you very much, Philip. And the next presentation, the second plenary talk, is by Randy Hewlett from Rice University. This year, he's celebrating his 35 years at Rice, right? Educated at Stanford and MIT and then NIST. That's where he actually started his work on laser cooling of ions at that time, but he is, of course, most famous for his work on laser trapping and cooling of atoms, where he was the first to realize BEC in atomic gases with attractive interactions, and also first to realize a degenerate Bose-Fermi mixture, and the first to observe in ultra-cold atoms to observe antiferromagnetic order in Fermi-Hubbard model. Distinguished career, many awards and prizes, the Rabi Prize of APS, the Lamb Medal, highly prestigious medal. And let me pass the stage to Professor Hewlett.
All right, thank you very much.
You can share your slides.
Thank you very much, Alexei. How's that? Can you see it?
Not yet.
Okay. Not sure why. Let me try sharing my screen again.
And in the meantime, I can
continue
listing your awards, and academy memberships.
Let's see. So I think you should be able to see that. Is that right?
We are seeing a collection of slides, but not the presentation mode. Yes, now we see it.
It's fine.
Okay, great. All right. Thank you, Alexei. So if I can be heard and seen and the slides
Yes.
are coming through, good.
Yes.
All right. So I'm going to be talking about a topic that's part of this second quantum revolution. We've heard a lot about that in the last decade or so. People have been working hard and making great advances on making general purpose quantum computers that can tackle certain problems with algebraic scaling and rather than exponential, as in some particular specific problems with digital computers. So the main effort in this quantum revolution has been to develop qubits that can be scaled, arrays of qubits that can be scaled up. And this is proven to be quite difficult and challenging. And people are making progress, but it's and there's great interest in seeing that progress, but things are not, we're not realizing general purpose quantum computers as of yet, in my opinion. It depends a little bit on your definition, I suppose. The work I'm going to be talking about today is related, but it's a simulation of a quantum system of a quantum material, electronic materials, with ultra-cold atoms, where the atoms are stand-ins for the electrons in the material, and we manipulate the potentials that these atoms, these quasi-electrons, see by making standing waves of light that are formed by what we call optical lattices. So, this conference, Laser Physics, has been a cornerstone reporting advances in lasers over the last 20 or 30 years. And I can remember a number of conferences that were tremendously exciting. I remember Trondheim, Norway, which here I am sitting in Houston, quite a difference from Trondheim in many respects. So, but lasers, nonetheless, even though they become a tool, and with the actual development of lasers being refined, the there's a lot of applications now of lasers that have drawn the general public. I was in Paris a couple of months ago, and I happened to cross this store on one of the streets in Paris, in a small neighborhood, Maison du Laser. And the Maison du Laser, turns out it's they use it for cosmetic surgery and removing unwanted hair. So, but it struck me when I saw this sign, Maison du Laser, and kind of emphasizes, I guess, that we've captured the public's imagination, and people are interested in exactly what these things do and how they do it and what they can be used for. So I'm not going to be talking so much then about lasers. I'm going to be talking more about this quantum simulation of a one-dimensional material in which one can observe spin charge separation. And I'd like to acknowledge all the experimentalists at Rice who've worked on this project, and I'll talk a little bit about them later. And also, we've enjoyed a couple of really great theoretical collaborations, one with Shiwen Guan and his group in Wuhan, China, and also with Thierry Giamarchi in Geneva. So here are some reasons why quantum simulation has become so popular and so powerful to be able to describe electronic materials of varying kinds. So the idea is that you realize some Hamiltonian, you vary the parameters of that Hamiltonian, and you can very quantitatively, precisely measure the properties of the material by varying things like interactions, lattice hopping, temperature, dimensionality, geometry, etc. So just about any of the properties of an electronic material we can both simulate with ultra cold atoms being the stand-ins for the electrons, and then we can vary these various parameters that influence the properties of the material. So some examples are quantum magnetism and exotic superconductivity. These are two topics that we're working on actively in my lab. Strongly interacting 1D systems. That's what I'll talk about today. Quantum criticality, disordered insulators, topological matter, and various other kinds of applications. So this is some work that we did about 5 or 6 years ago on antiferromagnetism in the 3D Hubbard model. It shows the static structure factor, S of Q, as a function of interaction strength in the Hubbard model. U is the interaction, T is the hopping. And you can see at U over T of about 12, there's a peak. This is due to Bragg scattering of light, which is spin sensitive in the way that we arrange it to be. And so we can see that the onset of this antiferromagnetic checkerboard-like structure by doing these kinds of experiments where we do Bragg scattering of light. So this realization, and by others, has given us some new insight and some experimental tools for studying the Hubbard model, which is one of the primary models used to describe high temperature superconductors. So this is theory on the right, and the theory at the temperature we're at, the theory is just on the hairy edge of being able to do quantum Monte Carlo calculations. And so we're beginning to get into the realm where the experiments are actually leading the way, and the theory has to catch up. which of course, as an experimentalist, is the place we'd like to be. Okay, so these are the ground state sublevels of the lithium atom, the 2s1/2 ground state of lithium-6. Lithium-6 is a composite fermion, and we work with the lowest three levels as a function of magnetic field. This is the Zeeman effect. These are the various projections of the nuclear spin, and these numbers refer to the m sub f values. Now, these are therefore not really spin-a-half system. If I take two of these levels, like the one shown in red, this is not a spin-a-half, but rather a pseudo-spin-a-half system. So the spin really doesn't enter. It's just the fact that it's a different state in which the Pauli principle can do its thing. All right, so one dimension is particularly interesting for the following reasons. We can study the excitations and transport in this system by allowing in 3D, the electrons move around other electrons. So if there's some kind of excitation in the 3D gas of electrons, we generate quasi-particle-like excitations that are single particle-like and they're fermionic. And this forms the basis of the mean field Landau Fermi liquid theory to describe such a fluid. But in 1D, it's really quite different. In 1D, the electrons can move to the left or to the right, but they can't avoid their neighbors. So if this electron, let's see if I can, can you see that pointer? Okay.
Yes.
So is that right, Alexi? You can see? Good, okay. So if this electron moves to the right, it's going to bump that electron, that'll bump this electron, that'll bump that electron. So contrary to the 3D situation, in 1D, electrons necessarily, the excitations are necessarily collective. And in fact, they're sound-like waves that have linear dispersion and they're bosonic and form the basis of the linear liquid theory, Tamanaga linear liquid theory of excitations in one-dimensional system. Now, these particle hole excitations in 1D are, as I say, different than they are in 3D. You can also see the Landau Fermi liquid theory in 3D in terms of a three-dimensional Fermi sphere in which all the excitations take place on the surface of this Fermi sphere. And we can connect any 2 points by a line, imparted momentum Q, which is somewhere lying between 0 and 2kF. In one dimension, the Fermi surface is not a sphere, but rather it's just 2 points. The 2 points being 0 and 2kF, or minus kF and plus kF, where kF is the Fermi momentum. So in that case, for low energy excitations, and this is what in the circle is described by the Tamanaga linear liquid theory, these low energy excitations are linearly dispersing. So the energy is increasing linearly with momentum, imparted momentum. And it repeats itself every 2kF. So these excitations can be described as spin density waves and charge density waves. In the charge density wave system, in the holons, there's a vacancy created by this electron moving into its neighbor and that produces an excitation which propagates down this one-dimensional wire. Now, in the case of spin, there's an exchange process where this red upspin exchanges with a blue downspin, creating these spin defects in the otherwise antiferromagnetically ordered one-dimensional wire. So these spin-ons and hole-ons, the spin density waves and the charge density waves, they're sound waves. They disperse linearly. There are, in fact, they disperse at different speeds. So for the charge density wave, the interactions cause the excitations to move a little bit faster than they would in an ideal gas. And for the spin density waves, a little slower. So we have this weird effect where there are these two speeds. The charge part of the electrons move faster than the spin parts of the electrons. And that's the phenomenon known as spin charge separation, which is uniquely associated with one-dimensional low energy excitations. So there's been a number of observations of spin charge separation in electronic materials, including carbon nanotubes that were made in the lab of my late colleague, Rick Smalley, who won the Nobel Prize for his work on C60 molecules. But there have been other observations as well. These tunneling measurements in Jacobi's lab at Harvard, spin-on and hole-on dispersion with LPHYS'. I think this is particularly beautiful. You see the charge excitations, you can see the spin excitations, and you can map out the whole dispersion relation. So the issue, however, if one is trying to do quantitative comparisons with theory, is that in a solid state, this comparison is made difficult by the complexities of the Coulomb potential. And what I mean by that is the Coulomb potential is generally screened, and we don't know exactly what the screening function is. And so that uncertainty makes it challenging to compare with theory. And then there's the inevitable disorder and lattice defect. So these deficits in the ability to quantitatively compare with theory has led people to look into quantum simulation with cold atoms. The first was by the lab in Florence, Leonardo Fulani's lab. And the first author of that paper, this was his graduate work, was Guido Pagano, and Guido is my current colleague at Rice. That's a small world. But they used the ytterbium atoms. They measured using something called Bragg spectroscopy, and I'll say in a minute what that is. And they were able to see the shift in the speed of the charge mode with respect to the ideal gas. So the solid line is the ideal gas excitation spectrum, whereas the dash line incorporates the interactions. You can see there's a shift. This is just the charge density wave because there's no Feshbach resonance in ytterbium-173, and so they can't vary the interaction strength as you would like in order to quantitatively investigate these effects. Now in Manuel Bloch's group, very recently in the last couple of years, they did a deconfinement excitation. These are one-dimensional wires that are independent of one another, or reasonably independent at zero temperature. And And what happens is they send a laser beam to knock off one of these atoms, and that produces an excitation that two excitations, one corresponding to spin density wave and one to charge. So they're able to observe this fractionalization into spin-ons and holons. They're able to see the separation of spin and charge, but it was not a linear liquid because it's at a higher energy, and therefore there couldn't be any quantitative comparisons with a linear theory. So we set out to do Bragg spectroscopy of these low energy excitations by making a bundle of one-dimensional tubes. So this is a two-dimensional optical lattice in which with enough intensity, these one-dimensional wires are all independent of one another. And one can do one-dimensional physics. So we detect what we've done by using Bragg spectroscopy, which gives you the dynamic structure factor as of both momentum and energy by imparting momentum with two near resonant laser beams that are at a small angle. And that angle and the momentum of the wave vector of the beams determines how much momentum is transferred in this process that can be resonant at a frequency difference between these two laser beams of omega. So for us, Q is about 10 or 20% of the Fermi momentum. And it's possible to make both a charge density excitation as well as a spin density excitation by the charge density wave is excited by detuning these Bragg beams by a large frequency splitting between the two, a frequency detuning which is large compared to this splitting, or a antisymmetric excitation in which the splitting is equal and opposite. The detuning is equal and opposite between the up spins and the down spins. And so this is a way of being able to selectively excite either charge density or spin density waves. All right, this is the Bragg signal. So you can see the signal with the Bragg pulse present. It bites out a little chunk of this distribution of atoms. This is the tube axis in the horizontal direction. And we take first signal image and then a reference where there's no Bragg pulse, and we subtract the two. And when we subtract the two, you can quite clearly see the atoms that are excited out of the Fermi C and where they came from in momentum space. So this is the Bragg signal down here, this peak, this positive peak. And that's what I plot on the following graphs. Now, it turns out that this spin structure, the structure factor, the dynamic structure factor, is related to the total momentum transfer delta P. And so by measuring this signal, you can get something which is proportional to the dynamic structure factor. And that's what we've done. So as I mentioned, the spin density wave is excited with the symmetric, antisymmetric detuning from resonance. And it's proven more difficult to measure because this splitting between these two levels is only 80 megahertz. And 80 megahertz is comparable to the 10 megahertz spontaneous lifetime of the excited electronic state that we're exciting close to. So spontaneous emission has been a problem. But we figured out a couple of things since the last time I've been talking about this. And one is that we're using an ultraviolet transition instead of the red. instead of the usual 2s to 2p transition, we're driving the 2s to 3p in the ultraviolet. And this has about 10 times the narrower line width in the 3p state than in the 2p. And so the spontaneous emission problem is largely mitigated by doing this. So we have both the red lasers to measure the charge structure factor and the purple ones to measure the spin structure factor. And this is the result. So the red shows the charge density wave, and the blue shows the spin. And the important thing is the peaks are shifted as we change the interactions between the atoms. So both of these, the red and the blue labeled by 0, means that there's 0 scattering length, no interactions. This is an ideal gas. So this is this spin structure factor. This is the charge structure factor. And at 0 interaction, they should be the same, and indeed they are. Now, if you go up in interaction by increasing the scattering length, eventually you can see, I think, pretty clearly that there's a splitting that's interaction induced. So if we go to the, say, 500 Bohr, this in the spin case, it shifted down to lower frequencies or lower speeds, whereas in case of the charge density wave, which is shown here in this red dashed line, it's a little hard to see, it shifted to higher frequencies or higher speeds. So this is the spin charge separation. This is actually showing very graphically the effect. This is the peak of the structure factor, the function of interaction strength, both for the spin in blue and the charge in red. And you can see, I think clearly that the charge is getting faster with increasing interaction, whereas the spin is getting slower. And so we have this paradoxical effect that the spin and the charge degrees of freedom of the electron move at different speeds, and therefore they're going to separate spatially as well as in momentum space. So I should add that the blue dashed lines and the red dashed lines are theory worked out by Zhuan Guan and his group in Wuhan. So we've more recently been looking for the nonlinear linear liquid. I should add that the linear liquid, the dispersions that we've measured in this case, agree excellently, I would say, with the data. And this is because in the case of one-dimensional system like this, there's some symmetries that allow these the energies, the Hamiltonians, to be solved exactly. This is, in other words, integrable systems. There's some nonlinear effects that come into play with these gases, and that's because the momentum is not that small compared to the Fermi momentum, and the charge density wave will disperse differently depending on the momentum transfer. That difference is actually pretty small for the case of charge, but in the case of spin, it's actually pretty big. So this is evidence of some nonlinear effect in the linear liquid that could be due to a number of different things. How am I doing on time, Alexei? Can't hear you. You're muted.
Well, you have 10 more minutes.
Okay. Is that before questions or after? Okay.
Either way, yeah.
Okay, good. You guys got a couple hours, and I can get it done really well.
Well, yeah. If you finish a few minutes earlier, we'll have extra minutes for questions.
Okay, I'll try to do that. Okay, so the difference, I didn't really highlight it, but the fit of the theory, which are the solid lines, to the data, which are the points, is not that good if one examines it very closely. So you can see, for example, in this region, the solid line deviates from the data, and then here it's not so bad. But it turns out that this is the evidence, which is, I guess, I should point out in the spin case, it is particularly obvious that there is something wrong with the fitting with the linear theory, which are the dashed lines, in the data, which are the points. Now, it turns out that difference arises because of band curvature, which can be accounted for pretty readily. In other words, deviations from the linear dispersion. Or in the case of the spin mode, it turns out that backscattering is the culprit, and backscattering causes the dispersion relation to be nonlinear. And it was really a tremendous effort that the Wuhan group was able to calculate the backscattering effect in the spin mode. And you can see it's really pretty good. So the solid line is the theory including backscattering, whereas the dashed line is just the standard linear theory. And there's really quite a difference between those two cases, and really great agreement with when backscattering is accounted for. So there's also the so-called spin incoherent linear liquid, and this seems kind of obvious, but as you increase temperature, you begin to produce decoherence in the system, and there are this rising temperature causes first a subtle perturbation on the antiferromagnetic order and low temperatures. It becomes initially spin incoherent, and eventually it becomes at high enough temperatures both spin and charge incoherent. In other words, it becomes a thermal gas. And theoretically, this has not been really well explained or characterized. And so this data, actually, I think it's the first data on the spin incoherent case. And you can see the spin structure factor is, for different temperatures, is changing rather dramatically. And if you make the same kind of plot that I made before, showing the peak of the structure factor versus temperature, you can see that there's a spin charge separation at low enough temperature, but as you increase the temperature, there's a suppression of spin charge separation, and the spin and the charge modes basically have exactly the same dispersion relation. And that's because of the decoherence that has destroyed the long-range coherence, the longer range coherence in the system. It's never completely long-range ordered. All right, so I just want to finish up just saying a few things about the one-dimensional fermions that we've been studying at Rice over the last few years. And one of the big motivations is to realize the Kitaev model of Majorana fermions that is predicted to occur when you have a one-dimensional P-wave superfluid. So we've been studying P-wave pairing as much as possible in order to make this realization of, well, in the case of electronic materials, this is an ordinary superconductor, an S-wave, this the blue base, and by proximity, it induces correlations in this metal tube, and the Majorana fermions are predicted to be located at the two ends of the tube. A much simpler way of doing this doesn't require that proximity to the 3D superconductor or spin orbit coupling, is to make a directly P-wave paired superconductor. And this is exactly what we're trying to do now. Now, the big problem, it turns out, is that this is a phase diagram of the P-wave superfluid, and it's going through the BCS to BEC crossover. And actually, there is no BCS to BEC crossover in a P-wave. And there are different order parameters to the right and to the left. And these can be described in momentum space by either a gapped or a gapless a PX plus IPY superconductor. In other words, something that has topological order to it. And there's either a topologically trivial phase, which is the gapless one, or a more interesting topological phase, which is the gapped one. So we want to use some combination of these lowest going hyperfine sublevels in a magnetic field to be able to realize a Feshbach resonance for the P wave, and therefore to be able to tune the interactions in the P wave superconductor. So we've been doing that, and this is a 1+1 superconductor where 1 is these two lowest going levels, 1, 2, and 3. And this is the 1+2, and this is the 2+2. So this has a function of magnetic field. So these are the locations of the Feshbach resonances. They're all around 100 to 200 Gauss. And but the issue is that after about 10 milliseconds of hold time, you essentially lose essentially all the atoms. Turns out it's a 3-body recombination process, but there are ways that we are trying to mitigate that loss, which some other people are also engaged in this, both theoretically and experimentally. Particularly, I would say, Joseph Thywison in Toronto, and trying to, using an optical lattice to isolate the atoms to prevent the 3-body recombination effect. So I think I'm done, and I just want to acknowledge the people who did the work. This was Daniel Cavazos' PhD work. Daniel's now at the University of Chicago, and the other co-lead author was Ruin Senaratne. And Ruin is a research scientist in my lab and looking for a job. And Ashish Kaple. Ashish is a senior graduate student and contributed greatly to this experiment. So that's it. Thank you.
Thank you so much. Thank you, Randy. The talk is now open for questions. While people are thinking of their questions, Alice, do you want to?
I have a simple question. Yes. Concerning the part of your talk where you are measuring these structure factors for the charge and spin waves, can you give us a simple interpretation of what happens? That you extract some features like the peak and the shift of the peak with the interaction strength, and maybe one could also look at the width, I guess. And so do we understand the behavior as a function of the interaction strength?
Yeah, so not really, and not completely, I would say. It's a trade-off between the Pauli principle and interactions. So the structure factor depends on both. And so I would say that the fact that the speed decreases with the spin mode at a greater rate than the charge mode speed increases is a result of the Pauli principle between nominally adjacent upspins and downspins in the spin case. Is that addressing your question, or are you interested more in how?
And do you also look at the width or not?
We look at the entire structure factor, and that's fitted to get back up. So we look at the entire structure factor, and part of that is the width is the width of KF, but also there's inhomogeneous broadening, which is due to the fact that the density is not constant.
Okay, thank you.
You're welcome.
Okay, thank you. Other questions? I'm wondering, Randy, if you have your own take on quantum computing using cold atoms and optical lattices, analog versus digital. Do you have something to say? What do you see as a route to the future?
Yeah, I do definitely have an opinion about that subject. We've been making great progress, meaning the community, to understand certain electronic materials at a level that wasn't possible before. And this is the case with analog quantum simulation. With the it's compared to the I would say digital, for want of a better word, the digital quantum computing, or just general purpose quantum computing, is still working on the engineering phase of being able to scale up the total numbers of qubits. And until they can figure out a way to have a system which survives long enough, whose coherence survives long enough, it'll be very difficult to scale up. And so I think, that's the major issue right now. And there's a lot of effort going into it. But at the same time, with analog quantum simulation of the type that I described today, we're getting results now.
Okay, thank you very much. Any other questions? We are pretty much out of time. We are a little bit over time for the session, but it's okay. We have 27 minutes before the next session starts. We have a set of excellent seminars. I know Olga wants to advertise seminar 1. I want to advertise seminar 10. We'll have a continuation of the quantum engineering story, using photonic crystal fibers to engineer quantum states of photons. That's the first talk in the session that I will preside over, David Noah. If you want to say something, Olga, you need to unmute.
Well, everybody is welcome to our seminar. We'll have next talks on plasma physics, basically. So you are very welcome.
Okay, thank you, everyone. Thank you, Randy and Philip. And we'll see you soon. Yeah.
Thank you, Randy. Nice talk.
Yes.
Thank you. Thank you, Manuela.
Thank you for your talks. It's wonderful. And thank you to Alexei for chairing this session. Thank you.
Yeah, if people who really wanted to leave have already left, I'm tempted to share a joke with you, Randy. It's not really funny. It's just a little bit funny, and what makes it a little bit funny is the fact that it's a true